So hello everyone, this is Roshan, and today I will going to conduct the last session of this course, which is week 13. So there is no lecture on this week. This is actually an extra session that is conducted by me only. So that session is basically based on the problem solving session. There is no theory part left till there is lecture only till week 12. So this is an extra session. Yesterday I will inform you that today I will going to conduct one more session, which is only for the problem solving session. So today I will solve some problem related to the theory of failure, and later on I will solve a few problems based on the thermoelasticity. So let's start today's session. So today's session is basically full problem solving session. So first there is one question more that is based on the theory of failure. So first I will write the question. So yesterday I will solve. I had solved whole problem based on the theory of failure, and few questions were still left. So the left question I will solve today. So this is one of the important question based on the theory of failure. So the question is that is problem first for today's session. Yeah, problem one. The dimension, the dimensions of an, the dimensions of an overhang, the dimensions of an overhang crank are given in figure 4.41. The force P, the force P acting at the crank pin, the force P acting at the crank pin is 1 kilonewton. Sorry, this is already shown in the figure, so I just write the figure. The crank is, the force P acting at the crank pin is 1 kilonewton. The crank is made of steel. The crank is made of steel whose yield stress in tension is 1 kilonewton. Okay, and the factor of safety taken here is 2, and the factor of safety is 2. Using maximum shear stress theory, using maximum shear stress theory of failure, determine the diameter D at section XX. Determine the diameter D at section XX. So let me first draw the figure, then I will explain the question. So figure is, so there is a crank, this distance is 500 mm, And this distance is where the load P is applied. This distance is 50. And this distance is 25. And the section XX from where we have to calculate the diameter is 100 mm. Okay. And the cross-sectional view of this crank is also given. So from this point, load P is acting. If we see the side view of this cross section of this crank, we see the load is acting in this way. And here also there is a hole. Okay. So this is a crank which is shown in the which is given in the question. And this is the diameter D, which is we have to find. Okay, so I'm repeating the question. The dimension of an overhead crank are given in the figure. So this is the dimensions, and this is a overhand crank, which is given in the question. The force P acting at the crank pin is 1 kilonewton. P is mentioned here, which is equal to 1 kilonewton. The crank is made of steel whose yield stress and tension is 1 kilonewton, and the crank is made of steel whose yield strength and tension is 1 kilonewton, and the factor of safety that is to be taken in this question is 2. The question is using maximum shear stress theory of failure, determine the diameter D at section XX. So this is a section, and here, so we have to find the diameter of the crank. What is the diameter of the crank based on the maximum shear stress theory? So let's solve this question. So first I write the given values of some parameter. So here it is already given that the load P is equal to 1 kilonewton. SYT is equal to 400 Newton per mm square. And factor of safety is to be taken here is 2. So first we have to calculate, because here we have to use the maximum shear stress theory. So first we will calculate the permissible shear stress. Okay. So permissible shear stress is given by permissible shear stress, that is sigma ys, which is nothing but half of the sigma, sorry, sys, which is nothing but half of syt, which is again equal to 0.5 into 400, that is 200 Newton per mm square. Okay. So for permissible shear stress, that is tau max is given by sys upon factor of safety. So it will become 200 upon 2, that is 100 Newton per mm square. So I hope you are understanding this question. In between, if you have any doubt, please write in the chat box here, or you can also unmute yourself so that I can listen you. So first, I have found the value of tau max, which is a permissible shear stress that can maximum it can sustain without any failure. Okay, so first I have calculated the value of maximum shear stress which it can handle. The next is, because here load P is acting in this way, so here due to this load there are two stresses will develop. The first is bending stress and the second is torsional stress, because you see in this figure load P is acting in this way, so it will actually, this is a your overhand crank and load P is acting this way. So if you see from this side, so you can see that here is a crank, and one load component actually produces torque, and the other load component actually try to bend this crank. So we have two different forces acting on this crank. The first is moment, and the second is bending moment, and the second is torque. So we have first calculate the bending moment and torque for this problem, and then using that we will find the value of permissible bending stress and torsional stress. So let's calculate first the bending moment. So the section here, the section of the crank pin at x-axis is subjected to combined bending and torsional moments. Combined bending and torsional moments. At the section x-axis, bending moment MB is, so we have to first calculate the value of MB. So what is MB here? So you can see in the figure that this load P will cause a bending moment about this x-axis. Okay, so we have to calculate the bending moment first about this axis. So this is your crank, and here this is the crank actually acting here, and from so this is the crank. I just show you through some pen. Yeah. So yeah. So this is your crank. This is your crank pin, and here a load is applied. Actually, if you see in the figure, a load this way is applied. Okay. So if you see from this point, that is from the point of pin, crank pin, you see a bending moment about this axis, x-axis. This is the x-axis, and this is the load acting. So about this point, there is a there will bending moment actually happen about this point. So what is the distance of this bending moment? So this is the distance. This is the location of the crank pin. So this distance is the uh, distance from where the about which from this section x-axis, and this is the point of bending moment. This is the point of load P. So P into this distance, perpendicular distance, will give us the bending moment value. So what is the distance here? So this distance is, let me check. Yes. So this distance is, first we have to calculate this distance because load P is acting here. So 50 plus 25 plus 100 into P. And what is P here? 1 kilonewton, that is 1000 Newton. So MB is given by 1000, that is P into 50 plus 25 plus 100, which is equal to 175 into 10 to the power 3 Newton mm. Now the torsional moment MT is given by, so MT, yeah, MT. So MT, you can see in this figure again that this is the load and this is the perpendicular distance from where it induces some torque about this axis. So we have to find the that torque. So the torque is given by P into that distance, that is 500. So this distance into P. So that is 1000 into 500. And one thing I would like to mention here that so the, sorry, so this is 1000 into 500, which is equal to 500 into 10 to the power 3 Newton mm. Now using that moment and torque, we will calculate the value of bending stress and torsional stress. So the torsional stress is nothing but shear stress. So first we will calculate the bending stress about x-axis. So bending about x-axis is nothing but the bending stress actually, which is given by the bending formula. It is mby upon I. And here MB is actually calculated above. So it's 175 into 10 to the power 3. And Y here is the distance from the centroid to the top of the surface, that is d by 2. So d is unknown here, that's why I'm writing it as it is, that is d by 2. Next, I, moment of area, pi d to the power 4 of a circular cross section is given by pi d to the power 4 upon 64. So it will become 1782. If you calculate this, it will finally give us 1782.54 into 10 to the power 3 upon d cube Newton per mm square. So this is the value of bending stress about x-axis. Now we have to calculate the shear stress due to torque. So shear stress is given by mt, that is torque, into r, that is d by 2 upon j. J is the polar moment of area of a circular cross section, which is nothing but pi d to the power 4 upon 32. So it is given by mt is already calculated above, 500 Newton to the power 3 into d by 2 into d by 2 upon pi d to the power 4 upon 32. If you calculate this, you will get 2546.48 into 10 to the power 3 upon d cube Newton per mm square. Okay, so this is the value of shear bending stress and shear stress due to the bending moment and torque generated due to the load P. Now we have to calculate, because here we have to use in the question it is mentioned that we have to use here maximum shear stress theory. So that's why we will calculate the maximum permissible shear stress. So maximum shear stress is given by, we will simply use the formula for the Mohr circle to find the maximum stress, maximum shear stress. We simply use the concept of Mohr circle, that is tau max is equal to root over sigma x upon 2 whole square plus tau whole square, which is nothing but 1782.54 into 10 to the power 3 upon 2d cube whole square plus 2546 upon into 0.48 into 10 to the power cube whole square upon d cube whole square. Okay, so if you calculate this, so I'm just write the final expression that I get after calculating these values. So the final value that I get is 2697.95. You can also calculate by yourself. If there is a mistake, please tell me so that I can correct here. Into 10 to the power 3 upon d cube Newton per mm square. Okay, so this is the maximum shear stress that we get in terms of diameter. And the question here is, we have to find the diameter, maximum diameter, using the maximum shear stress theory. So it is, we have already calculated the value of maximum permissible stress, and that is equal to 100 Newton meter square, which is, so before failure to happen, the maximum shear stress due to this load must be less than the maximum permissible stress. Maximum permissible shear stress, that is 2697.95 for, so here we are using maximum shear stress theory. Using maximum shear stress theory, using maximum shear stress theory, 2697.95 into 10 to the power 3 upon d cube must be equal to or less than equal to 100. So the maximum diameter that it can be built, the maximum diameter is given by, if you calculate this, you will get d is around 29.99 mm, which is approximately 30 mm. So this is the final diameter for this question. Okay, I hope you understand this question. So this question is nothing but what this is a very basic question, but a good question. Using this question, a simple question will easily build that will be useful in your assignment problem or in your final proctor exam, which is going to happen in the last week of October. So this is a very good question at the exam point of view. So this question is telling about the maximum shear stress theory. So here there is a crank, overhang crank is given and a load P is acting such that it induces some bending moment and torque both at the section XX. And we have to find using maximum shear stress theory, we have to find the what is the diameter of the this crank, diameter of this crank, so that the maximum yield stress is in tension is 1 kilo Newton. So we are using that concept only. So first we have found the value of maximum torque and maximum bending moment that it can sustain. Then using that we will use the torsion formula and the bending formula to find the value of bending stress and shear stress. And then using the concept of Mohr circle, we find out the maximum shear stress and relate it with the permissible shear stress. And using that we easily find out the value of diameter D of this problem. So this is all about problem number 1. So yesterday I also solved some problem related to theory of failure. I think yesterday I had solved around 4 questions, and today one more question is here. So I think that these 5 questions are sufficient for you to understand the theory of failure easily. And most of the time, you see that most of the time in the exams, only 3 theories will asked. That is distortion energy theory, then maximum shear stress theory, and maximum principal stress theory. So these three theory out of 6 theories are very important for the exam point of view. And I had solved almost 5 questions related to this theory. So if you missed the yesterday class, I think you should go to the recorded lecture of this previous session and see what is solved there, because that question are very good question at all. So I hope you will be better understand, so that it will be easier for you to get good marks in the exam. So this is question number 1. Now I will solve some problems related to thermoelasticity. So thermoelasticity in the field of solid mechanics is also one of the important concept, because most of the time thermal strain, we have to calculate thermal strain, thermal stress due to temperature change in the material. We have to calculate it. So that topic is also very important for the exam point of view. So I will solve around 3 to 4 questions here based on the available time. So I am remaining around 1.5 hours. So within 1.5 hours, I will solve around 3 to 4 questions based on the thermoelasticity. So let's start problem based on thermoelasticity. So this is problem number 2 for today's session. Problem 2. So the question is, what will be the pressure? What will be the pressure that has to be applied? That has to be applied to the ends of a steel wire of length 5 centimeter to keep its length constant when its temperature is raised by 50 Kelvin. For steel, Young's modulus is 2 into 10 to the power 11 Newton meter square, and the coefficient of thermal expansion is 1.1 into 10 to the power 5 per Kelvin. Okay. I'm repeating the question. What will be the pressure that has to be applied to the ends of a steel wire of length 5 centimeter to keep its length constant when its temperature is raised by 50 Kelvin? So ends of a steel wire of length 5 centimeter, we have to keep the length constant, and we have to find what will the pressure rise in the steel wire so that the temperature is raised by 50 Kelvin. So let's solve this question. So solution of this question is, so given here that delta T is equal to 50 Kelvin, that is change in temperature is 50 Kelvin, and Young's modulus is given as E equal to 2 into 10 to the power 11 Newton per meter square, and alpha, which is the coefficient of thermal expansion, is given by 1.1 into 10 to the power minus 5 per Kelvin. So we already know from the theory that we have to calculate the thermal strain due to temperature change. So thermal strain in the wire is given by alpha times delta T. Okay, I already told in the starting, that is in the previous session lecture, that thermal strain due to temperature change is given by alpha times delta T, where alpha is the coefficient of thermal expansion, and I write there T, which is the temperature change, and here delta T is the temperature change. So please don't confuse with delta T and T. So delta T here is a change in temperature. So alpha delta T, that is alpha is here 1.1 into 10 to the power minus 5 into delta T is 50. So it will become, yeah. So this is the thermal strain. Now we have to calculate the pressure. So required pressure. So this is basically thermal strain, epsilon T. Required pressure is given by E into thermal strain. So E here is 2 into 10 to the power 11 Newton per meter square into 1.1 into 10 to the power minus 5 into 50, which is coming out to be 1.1 into 10 to the power 8 Pascal. So this is the required pressure, because due to temperature change, if you increase the temperature of the steel bar, and you want the length to be fixed, that means it doesn't change due to temperature change. So that due to this, if we fix the length, that means we are fixing from both the ends. So in that case, there is some pressure induced due to the temperature change, and that pressure change is given by the thermal strain in terms of Young's modulus. So it is given by E times thermal strain, and thermal strain we already calculated using the formula, that is alpha times T, alpha into delta T, and we finally find the value of required pressure 1.1 into 10 to the power 8 Pascal. Therefore, the value of pressure that is to be applied to the ends of steel wire so that its length will remain fixed is 1.8 into 10 to the power 8 Pascal. So the value of pressure that has to be applied to the ends of a steel wire is 1.1 into 10 to the power 8 Pascal. This is the final value of this question. So this is all about question 1. This is a very simple question. Now I will solve more problem based on thermoelasticity, which is the complex one, which is a very good question. So please give attention here. And in between, if you have any doubt, please, I tell you that please write in the chat box, or you can also unmute yourself so that I can listen you and you can ask your doubt here. Because if you miss that part and you know nothing, and if you suppose if you are not understanding clearly, then it will be difficult for you to perform better in the final proctor exam or even in the assignments, because assignment and proctor exam are very uh, in that exam there is a very good questions. So if you know the basics, you will then better perform. Otherwise it will become difficult for you to perform better. So that's why this session is conducted by the NPTEL team, so that you can learn in even in a better way, because every time theory will not work unless you solve some numerical problem. So that's why this session will conducted by two scholars. Okay, so this is the question 2. Now move on to the next problem, that is problem 3. So the question is, for the assembly shown in figure, find the stress in each rod if the temperature rises 30 degrees Celsius after a load W equal to 120 kilonewton is applied. So there is a figure also in this question. So I will draw the figure first. So I think the figure will not go in that space. So I will draw in the next page. So this distance is given as 2.5 meter. This distance is given as 1.5 meter. This is a bar of steel with length is 1.5 meter. Area is 320 mm square, and Young's modulus of the steel bar is 200 gigapascal. Okay, This is a bar of bronze whose length is 3 meter. Area is 1300 mm², and E is 83. Young's modulus is 83 gigapascal. Okay, and this length is given as 1 meter. And here there is a weight W. So I'm repeating the question. For the assembly shown in figure, find the stress in each rod if the temperature rises 30 degrees Celsius after a load W equal to 120 kilonewton is applied. So we have to find the value of stress developed in each rod, that is in the steel as well as in bronze rod, if the temperature rises 30 degrees Celsius. So here changing temperature is given as 30 degrees Celsius and a load W which is equal to 120 kilonewton is applied. A load W which is equal to 120 kilonewton is applied. So let's start the solution for this question. Okay, so first we have to calculate the value of thermal stress for this question, which is delta T. Thermal stress is given by alpha, not thermal stress, change in length due to temperature change. So we know that the value of thermal stress, which is nothing but delta T upon original length, is given by alpha times delta T. So from here, delta T is given by alpha L delta T. So this is the change in length due to temperature. I'm writing here. So delta T is the change in length due to temperature change. So first I will find the value of change in length due to temperature change of the steel bar and then of the bronze bar. So delta T of steel is given by alpha of the steel, L of the steel, and delta T, which is nothing but alpha is given as alpha is same coefficient of thermal expansion. No. Alpha of the steel is given as 11.7 into 10 to the power minus 6. Length of the steel is already mentioned 1500 mm. And so I am converting all the units in mm, and delta T is 30 degrees Celsius. So it will come out to be 0.265 mm. So alpha of the steel and alpha of the bronze is also mentioned in the question. Alpha of the steel is 11.7 into 10 to the power minus 6, and alpha of bronze is 18.9 into 10 to the power minus 6. Next, delta T of the change in length due to temperature change of the bronze bar is equal to alpha of bronze, length of bronze into delta T. Alpha of bronze is 18.9 into 10 to the power minus 6 times 3000, because length of the bronze bar is 300. Okay, so 3000 mm into 30, so it will coming out to be 1.701 mm. So we calculated the value of thermal strain change length due to temperature change of the steel and the bronze bar. Now if we give the heat, that is if the temperature change of the system, then there will be some stress will develop in both the section, in both the steel and the bronze, and due to that stress, uh, there will some stress generated, and we have to find that value of the stress. So we know that using the concept of total change in length, because total change in length will be a constant. So therefore, thermal stress due to steel minus thermal stress plus thermal stress due to elastic part. So that is, I'm writing here delta T, that is change in length due to temperature in the steel bar, plus change in length in the steel bar upon this ratio. So first, before doing this, I will draw one figure so that you can better understand what I am talking about. So here there is a fixed pin support. This is the bar we have. Okay, and here steel bar is there. So some load P stress, load P is acting, and here the bronze is there. So also some reaction force P of the bronze is acting. So here is pin support, and this length is given as 2.5 meter and 1 meter. So it is, and here also reaction force is coming. W is acting downward, which is equal to 120 kilonewton. That is 120,000 Newton. This distance is 1 meter. This distance is 2.5 meter, and this distance is 1.5 meter. So when this load is applied, so there is some, and if we change the temperature of the system, there will be some thermal strain is developed in the system, and it will be look like this. So here the strain is developed due to change in length due to temperature change in the steel bar plus change in length due to steel bar due to elastic property of the steel. This is the change in length due to the weight, and this is the change in length of the bronze bar due to temperature change plus change in length of the bronze bar due to the elastic property of bronze. Okay, now using the concept of ratio, so this, if we see the value of this one, so this two triangle, if you see this two triangle, this become quadrant triangle. So using the concept of quadrancy, we can find the ratio is equal. Ratio of this two length will be same, and this distance is okay. So this distance will become delta T Now we are using the concept of quadrancy of this triangle plus this triangle. Okay, plus this triangle. And we know this triangle is of length 1 meter, and this triangle will be of length 4 meter. So from here, from above figure, we can say that delta T of steel plus delta of steel upon 1 is same as delta T of bronze plus delta of bronze upon 4. Okay, so from here, delta T of steel plus delta of steel equal to delta T of bronze upon 4 plus delta of bronze upon 4. So delta of T of steel is already calculated above, that is 0.5265. 0.5265 plus delta of steel due to the load, due to the elastic property, is given by PL upon A, because we know strain is given by P upon A. So delta L is given by PL upon A. Using that concept, we are writing here. So P upon A is nothing but sigma, stress in the steel. So sigma L upon E of the steel equal to 1.701 delta T of the bronze is already calculated above. That is 1.701 upon 4 plus sigma L upon 4E, because you can see in the question that E is given as 83 gigapascal for the bronze of the bronze. Now we are calculating this 0.5265 plus sigma L upon, if we write the value, sigma of steel into length of the steel bar is 50 mm upon E is 200 gigapascal, which is 200 into 10 to the power 3, because we are converting all the units in megapascal, that is Newton per mm square. So 200 gigapascal equal to 0.425 plus sigma of the bronze into 3000, because the length is 3 meter, 3000 upon 4 times 83,000, because we have to convert all the units in megapascal. If we calculate this, the final value that is coming out to be 0.0075 sigma of the steel minus 0.009 sigma of the bronze equal to minus 0.10125. Okay. So this is the final equation that is coming out to be. Now we have to find the relation of sigma of steel and sigma of bronze, because we have two unknowns here, that is stress in the steel bar and the stress in the bronze bar. And to solve for these two unknown, we have here only one equation. So we have to find one more equation. So we will find using the moment about point A. So this is the point A of this question. So we will take moment about this point A. So this, because this is a fixed end support, so there is moment about A is 0. So moment about A is taken to be 0, which is given by P of the steel, that is load of the steel, times 1 plus P of the bronze times 4, P of the steel plus 4 times P of the bronze equal to W times into 2.5 meter. And W is given as 120 Newton, 120 kilonewton. So it is given by 120 into 10 to the power 3 kilonewton into distance, that is 2.5. And P of the steel is given by sigma S of the steel into area. And area of the steel bar is already given 320 mm square, plus 4 times sigma of the bronze into area. And area of the bronze bar is given 1300 mm, which is equal to 2.5 into 1201. plus 30 mode. If we calculate this, we are coming out to a relation between sigma of the steel and sigma of the bronze, which is 16.25. Sigma of the bronze plus sigma of the steel equal to 937.5. So from here, sigma of the steel is coming out to be 937.5 minus 16.25 sigma of the bronze. So using equation 1, we have, wait for a second, I have yeah. So here using equation 1, so we have equation 1 here. We will put the value of steel stress in the steel in terms of bronze in equation 1. Then we will get point sorry 0.0075937.5 minus 16.25 into sigma of the bronze minus 0.009 sigma of the bronze equal to minus 0.10125. Okay, if we calculate this, we are coming out to be 7.1325 equal to 0.130915 sigma of the bronze. So finally it coming out to be sigma of the bronze equal to 54.48 megapascal. And similarly, using equation 2, sigma of the steel is coming out to be 937.5 minus 16.25 into 54.48, which is coming out to be 52.2 megapascal. Okay. So this is the value of sigma of the steel. So the question is asking about, we have to find the value of stress in each rod if the temperature is rises by 30 degrees Celsius. So we already find the value of the stresses in each bar, that is in the steel as well as in the bronze bar. In the steel bar, 52.2 megapascal stress is induced, and in the bronze bar, 54.48 megapascal stress is induced. So this is all about question number 3. Now coming to the next problem, that is problem number 4. So this problem is also based on the concept of thermoelasticity. It's also one of the good question. So the problem 4 is, I'm writing the question. At a temperature of just wait for a second. At a temperature of 80 degrees Celsius, a steel tire a steel tire 12 mm thick and 90 mm wide that is to be strung that is to be strung onto a locomotive driving wheel onto a locomotive driving wheel 2 meter in diameter just fits over the wheel which is at a temperature of 25 degrees Celsius. Which is at a temperature of 25 degree Celsius. So the question is determine the contact pressure. Determine the contact pressure between the tire between the tire and wheel between the tire and wheel after the assembly cools to after the assembly cools to 25 degrees Celsius. Neglect the deformation. Neglect the deformation of the wheel caused by the pressure of the tire. Assume alpha is 11.7 micrometer per meter degree Celsius and E, that is Young's modulus, is to be taken as 200 gigapascal. I'm repeating the question. The question is, at a temperature of 80 degrees Celsius, a steel tire 12 mm thick and 90 mm wide that is to be strung onto a locomotive driving wheel. So a steel tire of 12 mm thick and 90 mm wide that is to be strung onto a locomotive driving wheel 2 meter in diameter just fit over the wheel. Okay, which is at a temperature of 25 degrees Celsius. Determine the contact pressure between the tire and wheel after the assembly cools to 25 degrees Celsius. Neglect the deformation. So this is neglect. Neglect the deformation of the wheel caused by the pressure of the tire. So here we have to neglect the deformation. We are assuming that there is no deformation in the wheel, and we have to find the pressure between the tire and the wheel. So suppose this is the wheel. So let's start with the solution. So suppose this is the wheel. This is the wheel. This is the wheel of 1200 mm. That is, sorry, 2 meter of diameter, that is 2000 diameter. And here we have a tire which is 12 thick, 12 thick, 12 thick and 90 mm wide. So we have to find the contact pressure between the tire and the wheel after the assembly cools to 25 degrees Celsius. So this is the front view of the tire. Now I'm drawing the rear side view of the tire. So it's look like this. So this is a side view of the tire, which is given in the question, that is 90 wide. So this distance is 90 This distance is already given in the question, that's 12 thick. This diameter of this given already given, that is 2000 of diameter. So here, if you see the cross section of this tire, we see that there is a force P acting outward from here also and from here also. And the steel pushes down some force, that is F inside. So from here, we can see that here also we are assuming that the deformation of the wheel caused by the pressure of the tire is negligible. And we have to find out the value of the constant pressure that is applied. Yeah. So since there is no deformation between the steel and the tire, sorry, between the tire and the wheel, hence there is no deformation between tire and wheel. This means that change in length due to elastic property of the tire is same as thermal strain change in length due to temperature change in the tire, which is equal to PL upon AE is same as alpha L delta T. So LL get cancel out. So from here, we will find the value of P, which is alpha delta T AE. Alpha is already mentioned in the question. That is 11.7 into 10 to the power minus 6 times delta T is 80 is the initial temperature, and when it cools to 25 degrees Celsius, so the temperature change is 80 minus 25 into area is given by 90 into 12, because area of the tire is 90 wide times 12 thick, that is 90 cross 12 into E, Young's modulus of the tire, which is 200 gigapascal. So we have to convert it in megapascal, which is 200 into 10 to the power 3. So this P value is coming out to be, when you calculate this, it will coming out to be 138996 Newton. Okay. One 138.996. If I calculate this, let me check again. 11.7 into 80 minus 25 into 11.7 into 90 into 12 into 200. Okay, so it's coming out to be 138,996 Newton. Now we have to find the value of pressure, that is, we have to contact pressure. We have to find the value of contact pressure applied. So from the figure, we can see that F is equal to 2P, and F is given by contact force. F is basically the contact force. F is given by PdL. So D into L is the area of the contact, and P is the pressure, contact pressure. That is equal to 2P. So contact pressure, so this is nothing but contact pressure, is given by 2P upon dl, which is equal to 2 times 138,996 upon dl, which is 2000, into length is given as 90. So it is coming out to be 1.544 megapascal. So the contact pressure between the tire and the wheel is given as 1.544 megapascal. So this is the final answer for this question. So this is all about question number 4. Now let's move on to the next problem, that is problem number 5. So this is again a very good question. So the question is, the rigid bar, ABC in figure shown here is pinned at B and attached to 2 vertical rods, and attached to the 2 vertical rods initially the bar is horizontal and the vertical rods are stress free. So the question is, determine the stress in the aluminum rod if the temperature of the steel rod is decreased by 40 degrees Celsius. Neglect the weight of the bar ABC. Neglect the weight of the bar ABC. Okay, so I'm drawing the figure first, then I will explain the question. So this is a bar of steel whose length is given as 0.9 meter. Area is given as 300 mm square. Young's modulus is given as 200 into 10 to the power 9 Newton per meter square. And alpha is given as 11.7 micrometer per meter degree Celsius. This is point A, this is point B, and this is point C. And the property of the aluminum bar is given as, this is aluminum bar. The property is length is 1.2 meter. Area is given as 1200 mm square. Young's modulus is given as 17 to 10 to the power 9 Newton per meter square. And the alpha is given as 23 micrometer per meter degree Celsius. Okay. This length is given as 0.6 meter and this length is given as 1.2 meter. So I'm repeating the question. The rigid bar ABC, so this is a rigid bar ABC. The rigid bar ABC shown in figure below here is pinned at B and attached to the two vertical rods. So you can see a steel rod and aluminum rod are attached at point A and C respectively. Initially, the bar is horizontal and the vertical rods are stress-free. Initially, when there is this rigid bar is kept in the stress-free configuration, so there is no stress between the horizontal as well as vertical rods. Now the question is, determine the stress in the aluminum rod if the temperature of the steel rod is decreased by 40 degrees Celsius. So there is a temperature decrease in the steel rod of by 40 degrees Celsius. So we have to find out what is the stress generated in the aluminum rod. Neglect the weight of the bar ABC. So we have to neglect the weight of the bar ABC. So we will solve this question first. So suppose if there is a temperature change in the steel bar, so there, because it is the temperature is decreased, so there is a change in length in the steel bar, and there is some thermal stress developed and trying to reduce the length of the steel bar. Because it is a decrease in temperature, whenever we increase the temperature, the steel bar gets expanded. But here the temperature is reduced, so there is a contraction in the steel bar. So I'm drawing the figure so that you may better explain this. This is our rigid bar. Okay. And there is some decrease in the length of the steel bar. That means the steel bar trying to reduce, and this is pinned support. This is pinned support and steel bar trying to get reduced. So this point will go upward. So that means, and there is a hinge support. So this point will go upward. So the final configuration after the deformation will be like this. That is, if we draw in the straight way, it will be like this. So this is delta of the point A, or we say delta of the steel. And this is delta of B at point B. This length is given as 0.6 meter and this is given as 1.2 meter. And there is a load resultant force acting due to the temperature change in the aluminum as well as in the steel bar. This is point B, A, and C. So there is a change in the length, that is delta A, and there is also a change in the length, that is delta B. Now using this concept, that is delta at point A upon 0.6 equal to delta of aluminium upon 1.2. Because the change in length in the aluminum is given by delta of aluminum upon 1.2. Delta at point A is given by 0.5 of delta of aluminum. Now here, if you see this figure, you can relate one thing, that this is the initial point and this is the change in length of the point A. This is delta of the steel due to the elastic property of the steel, and this is the delta of change in length in due to temperature in the steel. Total change in length in the temperature due to the steel. So from here, we can conclude that delta T of the steel minus delta S of the steel due to the elastic property of the steel is given as delta of the A value, total deflection at A. So it is coming out to be delta T of the steel minus delta of the steel is equal to 0.5 delta of the aluminum. Delta T of steel, we have to calculate this first. So delta T of the steel is given by alpha L delta T of the steel. Alpha is given as 11.7 into 10 to the power minus 6 into 900 into 40. This comes out to be 0.4212 mm. So using this, we finally reach out to the value of delta T of the steel, which is equal to 0.4212 minus PL upon AE of the steel equal to 0.5 PL upon AE of the aluminum, which is equal to 0.4212 minus P of the steel. Length of the steel bar is 900 mm upon 300 of the area and 200 gigapascal, that is 200 into 10 to the power 3 megapascal equal to 0.5 into P of the aluminium into 1200 upon 1200 into 70 gigapascal, 20,000. So this will become 28080 minus P of the steel is equal to 0.4762 P of the aluminum. This is our equation number 1. Now here again we have two unknowns and we have only one equation, so we have to find one more equation so that we can solve for this unknown. So here we have to take the moment about B equal to 0. Summation of all the moment about B equal to 0. Now summation of all the moments about B equal to 0, because there is, because this point is pin support, so there is moment, summation of all the moment here is 0. So 0.6 into P of the steel equal to 1.2 into P of the aluminum. That is P of the steel is given by 2 times P of the aluminum. So this is our equation number 2. Now using equation 1 and 2, we can conclude that 28080 minus 2 times P of the aluminum equal to 0.04762 P 0.4762 P of the aluminum. So load reaction force in the aluminum bar is given as 11340 Newton. Now we have to calculate the stress. What is the question here? So we have to calculate the stress in the aluminum rod. So stress in the aluminum rod, stress in the aluminum rod is given by sigma of the aluminum is given by P of the aluminum upon area of the aluminum, which is equal to 11340 upon 1200, which is equal to sigma of the aluminum is given as 9.45 megapascal. So this is the final expression. So this is the stress generated in the aluminum due to temperature change in the steel bar. That is given as 9.45 megapascal stress is generated in the aluminum bar. So this is the final answer for this question. I hope you are understanding this question. This is a very good question. Now, I am solving the last question for this session today. That is problem number 6. Yes. Let's begin this question. Oh, sorry. So problem number 6. This question is as shown in the figure below. As shown in the figure below, as shown in the figure below, there is a gap. There is a gap there is a gap between the there is a gap between the aluminum bar between the aluminum bar and the rigid slab that is supported by two copper beams, two copper bar. Sorry. As shown in the figure below, there is a gap between the aluminum bar and the rigid slab that is supported by two copper bars at 10 degrees Celsius. At 10 degrees Celsius, delta is 0.18 mm. Neglecting the mass of the slab, calculate the stress calculate the stress in each rod when the temperature in the assembly when the temperature in the assembly when the temperature in the assembly is increased to 95 degrees Celsius. Is increased to 95 degrees Celsius. For each copper bar, area is given as 500 mm square. Young's modulus is given as 120 gigapascal. And alpha is given as 16.8 micrometer per degree Celsius. For the aluminium bar, area is given as 400 mm square. Young's modulus is given as 70 gigapascal. And alpha is given as 23.1 micrometer per meter degree Celsius. Okay. So this is a question. So there is a figure also in this question. So first I will draw the figure, then I will explain it. This distance is 750 mm. Okay. Okay, fine. So I'm repeating the question. As shown in the figure below, so we have a figure below in this question. There is a gap between the aluminum bar and the slab and the rigid slab that is supported by two copper bar. So this is the rigid slab if you see in the figure. So this is the rigid slab which is supported by two copper bars. This one which is supported by two copper bars. And there is an aluminum bar with a gap of delta in between these two rigid these two copper bar. So aluminum bar is filled with a gap of delta value from the rigid slab. At 10 degrees Celsius, delta is 0.18 mm. So at 10 degrees Celsius, it is mentioned in the question that delta is 0.18 mm. Now the question again is, neglecting the mass of the slab, calculate the stress in each rod when the temperature in the assembly is increased to 95 degrees Celsius. So initially it is kept at 10 degrees Celsius. Now the temperature of the assembly is increased to 95 degrees Celsius. Now we have to find that when the temperature is increased, so the aluminum rod is also stretched and it will create some stress in this rigid slab. So we have to find the stress in each rod, that is in the copper rod and in the aluminum rod. And it is some values are given in the question, that is area of the copper bar is 500 mm square. E is, that is Young's modulus, is taken to be as 120 gigapascal. Alpha is taken to be as 16.8 micrometer per meter degree Celsius. And for the aluminum bar, area is to be taken as 400 mm square. Young's modulus is to be taken as 70 gigapascal, and alpha, that is the coefficient of thermal expansion, is taken to be as 23.1 micrometer per meter degree Celsius. So let's begin with the solution of this question. So first we have to calculate the delta T, that is the change in length due to temperature change in the copper bar, which is equal to alpha L delta T. So here alpha, it is mentioned in the question, it is equal to 16.8 into 10 to the power minus 6, and length of the copper bar is 750 mm times delta T, that is change in the temperature. So initially it is 10 and it is changed to 95. So 95 minus 10. So delta T of the copper is coming out to be 1.071 mm. Next, we have to find the change in length due to temperature change in the aluminum bar. That is delta T of the aluminum, which is equal to 23.1 into 10 to the power minus 6 into 750 minus 0.18, because there is a gap between and this distance is 0.18 mm. Okay, that's why we have to subtract 750 from we have to subtract 0.18 from 750. So this distance is 0.18 mm. So 0.18 mm, and the change in temperature is same here, 95 minus 10. So the final value that is coming out to be after solving is 1.472 mm. So we have calculated the value of change in length in the copper as well as aluminum bar when there is a change in temperature in between them. Now we have to calculate the value of stress in both the copper and the aluminum. This is the main aim goal of this problem, that is we have to find the value of the stress in the aluminum as well as the copper bar. So for this, first we have draw the figure one more time so that we will see how the strain is developed, that is how the deflection happen when the temperature is changed to 90 degrees Celsius. So this is suppose, so this is a rigid slab, suppose. This is our rigid slab, and here we have one copper, and there is a gap in between them, and it is given as delta. Now suppose after having increase in temperature, that rigid slab is shifted upward. First it will extend. In the initial case, what will happen? The aluminum bar is increases its length because there is a temperature increase. So in the first case, the temperature will increase due to temperature increase. There is an increase in length in the aluminum bar. Why? Because there is a gap in between in the initial phase. When the gap will be filled due to temperature change, then it induces some stress in the uh, in the rigid slab, and due to which the slab goes upward. So then the slab will be now this one. So this is the final position. So if you see that this is the initial position of the aluminum, and due to the temperature change, the final position of this aluminum slab is this one. That is, this is nothing but delta T of the aluminum. Now, because the copper bar is sorry, this is, I think, yeah. So this is delta T of the aluminum. Now, since the copper bar is fixed, you can see that it's fixed in the rigid slab. So as the rigid slab goes upward, the copper the copper, there is a change in the length of the copper bar also, because it goes upward, and due to the thermal stress developed between the bar and the slab, it will create some thermal strain. So due to thermal strain in the copper bar, suppose the copper bar now shift to this position, and this has become delta T of the copper bar. And due to the elastic nature of the copper bar, there is also some change, because the copper bar is assumed to be elastic, and due to the elastic effect, there is also change in length due to the copper bar. And because of the elastic nature of aluminum, there is also some elastic change in length. There is also some deflection due to the elastic nature of the aluminum bar, and it is delta of the aluminum. So this is the initial position, and this is the final position of the entire slab of the entire. This is the final position, and this is the initial position of the slab. I hope you are understanding. So this is the delta T of the aluminum. That is the change in initially the bar is kept here. That is, the aluminum bar is kept here. When the temperature is raised, first it will fill this gap. After filling this gap, it lift the rigid slab upward, and suppose at the final state it will reach here. So the final deflection of the aluminum top position from the initial case is delta T. So due to temperature change, of course. So this is the change in length due to the temperature change in the aluminum bar. And there is also some elastic change happen, which is delta of the aluminum, and there is a copper elastic and thermal change in length due to thermal and elastic change in the copper bar also. That is delta T of the copper and delta of the copper. So using this concept, we have write one relation, that is delta T is given as delta T of the aluminum is given as delta T of the copper plus delta of the copper, sorry, delta T of the aluminum is given as delta T of the copper plus delta of the copper minus delta of the aluminum minus delta of the T. So this is the total change in length due to temperature change in the aluminum bar. So from the figure, we can say that from the figure, we can say that delta T of the aluminum minus this length, that is delta T of the aluminum minus this length and minus this length will become delta of the copper plus delta T of the copper. Delta T of the copper plus delta of the copper. Now we are using the formula of this. It is all this change in length formula in case of the thermal strain also, and in the case of elastic strain also. So we are using the concept here, that is, it's already we already find the value of delta T of the copper and delta T of the aluminum. That is, delta T of the aluminum is 1.472 mm minus delta is given as 0.18 mm. Delta of the aluminum is given as PL upon AE of the aluminum, which is equal to delta T of the copper, which is already found. That is equal to 1.071 mm. 1.071 plus delta of the copper is given by PL upon AE of the copper. Now it is given as 1.472 minus 0.18 minus P is here. So what is the value of P? That is the stress resultant, or we say reaction force in the aluminum bar. So suppose copper, because copper is fixed at both the end at equal distance from the aluminum bar. So suppose it induces a reaction force F. So this one also induces reaction force F. And therefore, if reaction force F is induces from both the ends upward, so there must be a reaction force 2F, which is in the opposite direction, to be act in the downward direction to maintain the equilibrium. So from this, we can find that the reaction force developed in the aluminum bar is 2F, and in the copper bar is F. So from here, we can see that 2F into length. What is the length of the aluminum bar? Is 750 minus 0.18. 750 minus 0.18 mm upon area. Area is also given in the question. Area of the aluminum bar is 400 mm square upon 400, and Young's modulus of the aluminum bar is 70 gigapascal. So we have to convert it in megapascal, and it is given by 70 into 10 to the power 3, which is equal to 1.071 plus load of reaction force at the copper bar is equal to F. So I just simply write here F into length of the copper bar is 750 mm. That is 750 upon area of the copper bar is 500 mm square, and Young's modulus is 120 gigapascal. So 500 into 120 gigapascal, that is 120 into 10 to the power 3. Now if we calculate this, we will find that it's coming out to be 0.221 equal to 6.606 into 10 to the power minus 5 times F. So from here, if you calculate this, the value of F is found to be 3345.44 Newton. So I hope you are understanding. So what I am doing is simply, so this is a question where we have to find the value of stress in each rod. So for this, first we have calculated the length change, that is change in length due to temperature effect. That is, we are using the simple formula alpha L delta T for both the copper and the aluminum bar. If after calculating this, we have found that what is the change in length of each of the bar due to the elasticity and the temperature change effect. So we have found that using that relation here, and we are also interested to find the value of the resultant force that is acting on each of the bar, that is at the copper bar and the aluminum bar. So we are using the concept of equilibrium here. So suppose at the ends of the rod, though both the bar are of the copper material, so therefore if the ends of the rod are experienced F force upward, so in between, that is in the middle of the slab, a 2F which is acting downward, uh, reaction force that is 2F is acting downward for the aluminum bar. So we are using this relation, that is P of the aluminum is taken to be 2F and the P of the copper is taken to be as F. We are using that relation and we can find the value of the reaction force F. So using that, P of the copper will be now F, which is equal to 3344 3345.44 Newton, and P of the reaction force on the aluminum bar will be 2F, which is equal to 6690.89 Newton. But we have not. We will have also have to find the value of the stresses. So stresses is nothing but the force per unit area. So we are using that concept here, which is we already find the resultant force, that is reaction force acting on the each of the bar. So we simply find the value of the stress on the copper bar, which is equal to 3345.44 upon 500, which is the area of the copper bar, which is coming out to be 6.69 megapascal. And sigma of the aluminum bar taken to be as 6690.89 upon 400, which is coming out to be 16.73 megapascal. So this is the question that is asked in the given problem. What is the value of the stresses in each of the bar, that is in the copper bar and in the aluminum bar? So we found the value of these two stresses. So this is all about this question. So I think you have understood these questions which I solved today. So today I solved 5 questions. Yeah, sorry, 6 questions. Today I solved 6 questions. The first question, that is problem 1, is based on the theory of failure. Here we have to use the maximum shear stress theory. I already mentioned in the starting of the session that the 3 theories are most important theories. That is the maximum shear stress theory, maximum principal stress theory, and the distortion energy theory. Most of the questions will be asked from this theory only. So I think you will be you can solve as much problem as you can from this theory. So I already solved around 5 questions from these theories. Please go through these solutions of this question once again, so that you can easily capture all the concepts very easily, and you can apply it in the upcoming exams for this course. So the first question is based on the theory of failure. Then I will solve around 5 problems which is based on thermoelasticity of effect. So here also most of the time only single question will ask about the thermal stress and the total stress developed in the bar or beam. So I am solving here only the problem based on the beam problem. So you can also apply the same formula using the here I am solving only for the bar problem. That is a thermal effect in bar, but I have not solved any problem based on the thermal effect on beam. So there will be a question based on the thermal effect on beam also, but most of the time thermal effect on bar problem will be asked in the exams. So therefore I have solved just such type of question. So question number 2 That is problem 2 is based on the thermal expansion. So it's a very basic question. I think everyone can solve this such type of question, and most of the time, because the NPTEL will ask such type of easy question only, because you have many number of questions, and it's a limited time there. So that's why they preferred a smaller question, but with a conceptual one. So this is a good question, and is expected to become in the final proctor exam. Then I will solve question based on the multiple bar problem. So here two or more bar will be fixed, and suppose we increase the temperature in one of the bar, so we have to find the value of the thermal stresses in each of the bar due to the increase in the temperature. Or the opposite thing also, suppose we decrease the temperature, so there is a contraction in the bar, and we have to find the value of the contraction in the bar itself. So such type of question will always asked in the exams. So better you should go through once again if you're not understood completely here. So this question is also based on the thermoelasticity effect. Problem 4, 5, and 6 are one of the very good question based on the thermoelasticity effect. So I think before going to the final exam, you can please go through one more time this lecture, because this is the last session of this course. And in this session, I only solved the question. I have not told any theory part, because in this lecture there is no theory part left behind. So starting with the course of this session, starting the session for this course, I started with the simple stress strain concept. Then I go to the bending beams, then torsion of beam, twisting of beams, shearing of beams. We have solved many problems based on these theories. The shear stress theory, that is Timoshenko beam theory, Euler-Bernoulli beam theory, then concept of shear center, then concept of energy methods. Then in the starting of this lecture, that is bending of beam, layering of beam, twisting of beam. So I have solved many problems. So, and I have covered around 12-week session. On every week, I conducted one live session. And for you, if you missed any of the lecture, NPTEL team also posted the recorded lectures in the YouTube channel. So you can go there and watch the session which you missed which you already missed. So I hope this session will be very productive to you for the exam, for the final proctor exam, or even in the assignments. So in the assignments, you will have to submit the assignment on the weekly basis. So I took the session early. That is, suppose some assignment coming in the next week. So I have taken the session for this week in the previous week. So it will be useful if you come in the lecture and see the problem, understood the problems, and then go to the assignment and then solve the problems in that assignment. I do not completely solve the entire assignment problem, because it will not good practice, because I have to motivate you. I have to understand understand you, so that you can apply that concept in that assignment problem. Not exactly I am solving the assignment problem. So in between, if you because already 12 week has gone, so if you in between, if you have any doubt in the assignment now, because you have already gone through almost around 11 assignments, so you if you have any doubt in any of the assignments, so I suggest you that you can write in the YouTube channel where these lectures are posted. You can write in the chat box of any lecture. I will see on a regular basis. So if I found something, I will reply to that one. So that will be easier for you also and me also. And I will also send the link to that YouTube. I will write in the comment box of the in the YouTube channel, where all the PDF of this lecture, of this live session lectures, will be posted there. I will send you the link in the comment box. Okay. So I hope you all enjoyed the session very much, and this course is already a very good course in the mechanical engineering, and it's a basic course, and this course is very useful in understanding the higher level courses which you will do in your final year undergraduate courses. So this course will be useful in your research purpose, also in your placement purpose also. Most of the placement companies find the people who are well understood in the solid mechanics, because they are all even industry uses the solid mechanics part. So this course is very important in terms of your higher education, in terms of your placement perspective. In all the respect, this course is very useful for you. So thank you once again for joining this course. I am very grateful to be a part of this course as an instructor, and we have two instructors for this course. I hope you already know that. So you can join any of the session connected by these scholars. So yeah, so let's say goodbye. This is the last time I am here for this course, and this is the last lecture, which is the extra session apart from the 12-week lecture session I have taken here right now. So yeah, thank you for your patience and for your support throughout this course. Thank you. Bye bye. See you once again in the future. Thank you. Now you can leave the meeting.